everyone, thank you so much for clicking onto the video. Today's learning objectives are all to do with optical isomerism. So we're going to learn about how it's a form of stereoisomerism and occurs as a result of chirality in molecules. And then we're going to look at how an asymmetric carbon atom is chiral and gives rise to optical isomers, which exist as non-superimposable mirror images and differ in their effect on plane polarized light. And we're also going to learn about a racemic mixture or a racemate. So by the end, we should be able to draw the structural formulas and displayed formulas of enantiomers and also understand how racemic mixtures are formed and why they are optically inactive. Now we're going to talk about optical isomerism. So isomers are compounds with the same molecular formula but with a different structural formula. And stereoisomers are compounds which have the same structural formula but a different arrangement of atoms in space. And so stereoisomers are a form of isomer. And one type of stereoisomer that we have is an optical isomer. And this occurs when we have four different substituent groups attached to an asymmetric carbon. So we call this carbon a chiral center. And this occurs as a result of chirality in molecules. And this asymmetric carbon atom we call chiral, and this gives rise to optical isomers or enantiomers, which exist as non-superimposable mirror images, and they differ in their effect on plane polarized light. A mixture of equal amounts of enantiomers is called a racemic mixture or a racemate. And so, for example, we'll look at 1-bromo, 1-chloroethane. So it looks like this. So this is 1-bromo, 1-chloroethane. And now what we do is we reflect this. So if we draw an imaginary mirror line, then what we do is we reflect it. And this carbon here is called the chiral carbon, and we normally denote this by a star. And what it means is just that it has four different substituent groups on it. So when we reflect it, the image that is, the molecule that is formed is non-superimposable onto this one, as we'll see in a second. So if I flip this, so we get the mirror image of it. So the CH3 would be here, and then we would have a hydrogen here, and then we would have a Br, and here is the chiral carbon. You can see that these two images are not superimposable, meaning that they can't be placed on top of each other and fit. So for example, if you think about your two hands, if you try and put your left hand on your right hand in any way, it will never be the same. So you'll always have your pinky on your thumb or your thumb on your pinky. You can't get them to superimpose onto each other. And this is the same with optical isomers. They can never be placed on top of each other and be the same. And we can only get optical isomers from 3D drawings. So when we draw something as 2D, we can't get these optical isomers. So we need to know how to distinguish between optical isomers. And the way we can do this is by using plane polarized light. So first we're going to look at what plane polarized light is. So light vibrates in all planes perpendicular to the direction in which the light is traveling. You might have thought of it as a transverse wave. And so when the beam is passed through a special filter called a Polaroid, the light that emerges only vibrates in one plane. And so we call it plane polarized. So on a kind of diagram, you could have light that vibrates in all directions like this. And what happens after it emerges from this Polaroid is that we only get it in one direction. And so we call it plane polarized. Now, the only way to distinguish between enantiomers or optical isomers is to use plane polarized light. And if we pass this plane polarized light through the optical isomers, one will rotate the plane polarized light clockwise a certain amount. And this is called the plus or the dextrorotatory isomer, and the other will rotate the plane polarized light anti-clockwise by the same amount and is the negative or lavorotatory isomer. And the thing to know about optical rotation is that it can be measured using a polarimeter. So when optically active substances are made in the lab, they often occur as a 50-50 mixture. And what an optically active substance is, it's just a substance with a chiral center that we can get two enantiomers out of. And so because they occur as a 50-50 mixture, which is called a racemic mixture or a racemate, these racemic mixtures won't have any effect on plane polarized light. And so we call them optically inactive mixtures. And that's because you'll have the minus isomer as well as the plus isomer. So then one of the isomers will rotate it clockwise by a certain amount, and the other one will rotate it by the same amount but anti-clockwise. And so overall, there's no effect. Whereas what it's doing is that the plus isomer is rotating it clockwise by a certain angle of theta. And so this is the plus or the D. But then the other one is rotating it anti-clockwise by the same amount, so also by the angle of theta, and this is minus or L. And so overall there's no effect and they balance out, and so the plane polarized light just stays as it is, just vibrating in that one plane. So now I'm going to look at some questions. For question 1, which one of the following can exhibit both geometrical and optical isomerism? So first let's think about geometrical and optical isomerism. So geometrical is where we have a carbon double bond to another carbon, and there's a lack of rotation around this double bond, and so we can form E isomers or Z isomers. E meaning that the two substituent groups which aren't hydrogens are on opposite sides, and Z meaning that the two substituent groups which aren't hydrogen are on the same side. And then we get optical isomerism when we have this chiral carbon. So this carbon with 4 different substituent groups attached to it. And so we can form 2 optical isomers. So we can form one, and then we mirror it. And so that is the second one. And so first let's draw out these molecules. So for A, we have carbon double bonded to a carbon, and then to the right hand side carbon we have a hydrogen, and then on the other side we have a carbon with a hydrogen, and then we also have this CH3 and then this ethyl. So we have a CH3 here, and then I'm going to draw an ethyl over here. And on the left hand side carbon we have 2 of these methyl groups. So we have a CH3 and also another CH3. So this is our A. And then for B, I'm going to put it in different colours so you can see it better. So we have for B, again, honing in onto the double bond, we have a hydrogen, and then we have this ethyl. So we have CH2, CH3. So we have CH2, CH3. And then on the other carbon, we have a hydrogen here. And then we have a carbon that has a hydrogen on it, and also this methyl and an ethyl. So we have CH2, CH3, and also we have a methyl. And then for C, we have the carbon double bond to a carbon, and then we have 2 methyls on this carbon. And then on the next door carbon, we have 2 ethyl groups. And then for the last one, for D, this time I'm just going to draw it as a straight chain. So we have CH3, CH2, and then we have CH, and then a methyl group, And then we have a carbon, a hydrogen, and another methyl group. And then we have a carbon double bonded to another carbon with 2 hydrogens. And so now we've drawn out all the molecules, we should be able to figure out which display geometric and optical isomerism. And so first looking at A, we can see that we do have a chiral carbon, because this carbon here has 4 different substituent groups attached onto it. Because if we draw it slightly differently, we have a carbon with a hydrogen, and then we have this bit here, which is C4, and then we have 7 hydrogens, and then we have a methyl, which is this one here, and then we also have an ethyl. And so this is how we would draw it if we were going to look at optical isomerism. And so because this carbon has 4 different substituent groups, we get optical isomerism. However, when we look at the double bond, which is what the focus is for geometrical isomerism, we can see that because we don't have 2 groups which aren't hydrogen, we actually don't get optical isomerism with this molecule, because we have 2 methyl groups and this extra group here. And so we don't have geometrical isomerism, and so it's not A. And then looking at B, we can see that again we have this chiral carbon. So we have this carbon here, which is attached to 4 different substituent groups. And so this is the chiral carbon. And again, we can draw this as carbon with a hydrogen, and then we have this C4H7. So we have the same thing as we did before. And then we have a methyl and an ethyl. And so this forms optical isomers because we've got these 4 different substituent groups on this carbon. And so we can then mirror this optical isomer to form the other one. And now when we look at the double bond, we can see that we have 2 groups which aren't hydrogens, and they're also different. So we have this group and this group. And so therefore we actually get geometrical isomerism. And so our answer is actually B. But let's have a look at C and D anyway. So for C, we can see that actually we don't get optical isomerism because none of the carbons are attached to 4 different substituent groups. However, we do get geometric isomerism because we have 2 groups which are the same, so this one and this one, and then we have the other 2 groups which are the same. So then we can say whether this is a Z isomer or an E isomer. And then looking at D, this molecule is actually not drawn right because this carbon here only has 3 bonds. And so that's why we can rule out. So before I move on to question 2, feel free to click off the video and try it for yourself first. So butanone is reduced in a 2-step reaction using sodium borohydride followed by dilute hydrochloric acid. By considering the mechanism of the reaction, explain why the product has no effect on plane polarized light. So for the first bit of the question, you kind of have to know that it undergoes a nucleophilic addition reaction. But pretending that we don't know that, we could say that this C double bond O is planar. And we have these partial charges on the carbon and the oxygen. And because it's planar, that means that the attacking group has an equal chance or probability of attacking from above or below the planar C double bond O group. So the key thing is that this carbonyl group is planar, and so the attacking group has an equal chance of attacking from above or below this planar group, and so therefore we form equal amounts of so we have to remember equal, so they form equal amounts of each optical isomer or enantiomer, and so therefore we get a racemic mixture, which is basically a 50-50 mixture of each enantiomer. And because we know that one enantiomer will rotate light in one direction, so let's say one enantiomer can rotate plane polarized light by a certain amount in one direction. So we're going to say clockwise, whereas the other rotates the plane polarized light by the same amount, but this time we have it anti-clockwise. And so what we have is that the rotations cancel out. And so we have no overall effect on plane polarized light. And what we call this is we say that there is no optical activity. So the key things to remember are that we form equal amounts of each enantiomer, and this is because there's an equal chance of the attacking group attacking from above or below this planar carbonyl group. And so we form a racemic mixture. So one of the enantiomers will rotate plane polarized light by a certain amount clockwise, and the other will rotate it by the same amount but anti-clockwise. And so the rotations cancel out, and there's no overall effect on the plane polarized light. So we say that it has no optical activity. And a bit later on, we're going to learn about this reaction. And so actually, if we're going to answer this question in an exam paper, the attacking group is actually a nucleophile. And it's actually a H- that we get from the sodium borohydride. And this is a nucleophilic addition reaction.